this is the most useful form. So we're going to do the same thing with the reduction potential for oxygen. And I don't want to go over, I'm not going to go all the way back to Gibbs free energy. But you should be able to go from the Gibbs free energy expression for non-standard conditions and come up with this equation. Okay. Did that answer your question?
Yes.
So let's do the same thing before we shut this down. You're going to do either that derivation or the derivation of the oxygen couple. Now, so I'm going to leave this equation up here. This is your starting point. The Nernst equation in this form, which is the log form, which we're going to need, and we're interested in the oxygen couple. So E naught so the standard voltage, so at pH 0 is 1.23 volts for oxygen. And the reaction is so if I reduce oxygen, the product here is water. We're interested in that particular process because we're really interested in this to understand how redox processes are going to work in water. So we have to really understand the redox properties of the solvent itself. So it is the product. Now Q going to be equal to what?
1 over?
Well, what goes in the numerator?
This is 1.
Well,
It's just going to be 1 over.
yeah, we have to, well, first I want you to explicitly, it's going to be what? The pressure of O2 over the hydronium ion to the 4th power. And since when the oxygen bubbles come up in our electrolytic cells, just like the hydrogen bubbles in the electrolytic cells, they're produced at 1 atmosphere.
Wouldn't it be products of the reactor? I'm stuck on the
Oh, I'm sorry. Thank you.
Okay, so it's 1.
It is 1 over that, and the pressure of the O2 is in the denominator. Well, you very much. Yes.
Why would it still be 1 if water doesn't count? Wouldn't it just be multiplied?
Yeah. Well, yeah, the water, yeah, we just ignore the water. That's where the 1 came from. Because this is the product. So the products have a unit activity. The water's the solvent. Yeah. So it's given a unit activity of 1. Now the pressure of the O2, which belongs in the denominator, thank you very much. That was bad. Since PO2 is equal to that, since around 1 atmosphere, Q is equal to 1 over the hydronium ion concentration to the 4th power again, and that turns out to be so we end up with the same. We end up with Q having the same exact form as it had with the hydrogen couple, because we're talking about reduction in both cases. These are reduction potentials. So now I can plug that back into the equation, and E is going to be equal to E naught minus 0.0592 volts over 4 times the log of do the same thing we did before. We pull this through, and it's equal to E naught minus 0.12. And so now we've got it in the same form. If we see, you're going to be deriving one or the other, and you'll want to take all these same steps to show this explicitly. And then that is the pH, so we get and we got this linear equation for the potential as a function of pH. Under standard conditions, pH is 0. This drops out. We have our standard voltage of 1.23 volts, which goes down at the same rate that it does for the hydrogen. Okay? And that, this derivation, or the one for hydrogen, is going to be question 0 or somewhere. I'm calling it question 0 since it's not on the practice test. It's going to be on the test. Okay? And so, because this, if you understand this, you really understand a lot of the underlying properties. We can't discuss what happens in water without understanding this. Okay? And should I wrap that, or should I draw the I'll draw the thing.
So it's the pH first.
I'll do the graph in a minute. Yeah. What did you say? What was your question?
What's the pH first? For 1 mole.
For 1 molar solutions, pH is 0. So this drops out, just like it does, and we'll talk about the 0 voltage. In fact, when we go to the big problem about the what is the first problem, it's best understood at pH 0. It's more easily understood, and then you just look at the graph. Anything that has hydronium ions in it is going to be parallel to those lines we're generating in the graph that I'm going to draw in a minute. And anything that doesn't have hydronium ions in it is going to be linear, just a constant value. And that's what we will take advantage of when we come to understand why, for example, zinc is stable in water at pH 7, but it's not stable in acid.
Right.
So all those things fall into place. So I will do the graph very briefly. Yeah, I'll do the graph real quick.
You could wrap and then do the graph so people have the option of watching it.
Well, let's look at the graph right now, because we just derived everything we needed to do it. And then we'll wrap and go on to the next problem. Yes?
Your board is raised up.
It's raised up where?
It's raised up about 6 inches.
So it's no longer in the field? Was I just off camera?
Down a little bit more. Right there.
Now it's good?
Now it's good.
Damn, okay. We'll get a tripod.
Somebody's painted.
Megan likes software.
Yeah. Well, yeah, maybe we should, yeah, okay, let's stop it and then we'll do the graph.
Okay, it's all yours.
Here, go ahead and push stop.
What is it? This one?
Stop. Yeah, hold the camera though.